Should we start? All right. Hello, everyone. I'm Greg, co-founder and chief exec at undo.io, and we're going to talk all about race conditions and how to debug them, or specifically how to find them. It's kind of warm in here, isn't it? And it's like middle of the afternoon, so I think we'll go really fast in an attempt to keep everybody awake. If it's too fast for you, well, keep up. And then maybe there's some kind of race condition joke in there I can't quite find at the moment. Right. Yeah, I started talking about this stuff and thinking about this stuff when we sort of noticed at Undo, when we put out any kind of marketing content on race conditions, it seems to get more traction than other stuff. And I thought, well, I'll try and put out a paper and things. And I thought, well, I don't really fancy myself as an expert, so I'll ask a bunch of people. And I asked people I knew and trusted, and I put stuff out on LinkedIn and Twitter, and what do people do? And I got pretty much nothing back. And it kind of dawned on me that this is a significant problem, and there really is very little out there in terms of tools that can. There are tools that can help you, and we'll introduce them. We'll talk through those. But beyond the kind of really basic stuff, very little out there. So I think it's kind of a really underserved need. I'm guessing everyone who's come has come today because this has been some pain that they've recognised in the past. I always like, in all the talks that I do, my aim is to leave knowing more than when I came in, right? The best way to learn something is to teach it. So hopefully this is a little bit interactive, right? I think Yen said at the beginning of the day, questions at the end. But I'm actually quite happy for us to get questions, and not just questions like corrections or adding things in that I don't know about and probably other people don't know about. So interaction is good. Just generally, right? A bug. What is a bug? Race conditions are obviously a type of bug. Well, I've got expectations of what my program is going to do, and reality diverges from my expectations, right? And the process of what we call debugging, which is really about discovering the root cause of the bug, is to figure out where did reality diverge from my expectations. Often it looks a bit more like that. Or another way of thinking about it is we're making this jigsaw puzzle, right? And we run the program multiple times. We get clues. Every time we get a clue, we're getting a new piece to the puzzle, okay? And eventually the solution resolves itself, or maybe we're getting clues like Sherlock Holmes or whatever. I think what makes bugs in general hardest to find, I think there's two things actually. One is how long between the bug itself, right, those arrows diverging, and you noticing. Okay, and the longer that gap is, the harder they are. This is why assertions are a good thing, because they really narrow that gap between the bug itself and the failure mode, and it's why the worst kind of failure is always bad results, right, when the program's run to the end. And I think the other kind of vector here is how deterministic is the failure, right? Does it happen in the same way every time? Maybe it fails one time in 100, maybe it fails every time, but every time it fails in a different way. And then it's like I'm getting a piece for the jigsaw puzzle, and every time it fails, every piece for the jigsaw puzzle is of a different jigsaw puzzle. And that makes it really hard to see what's going on. And of course, life gets really hard when we're in the top right-hand corner here, right? We've got both non-deterministic and a long time between noticing and it failing. Of course, really fun when we get the Heisenbugs, right? And every time you try and get another clue, you change the behavior or the bug just goes away. And race conditions tend to live at the top right-hand corner of this little graphic, right? They are by definition non-deterministic, and they tend nearly always to be a long time between the problem itself and you noticing the assertion failure or the bad result or the crash. It's usually, they tend to be these kind of silent killers. We tend to corrupt some bit of state and not notice to sometime later. So that's why they're so hard, right? The top right-hand corner of this thing. Let me just define what I mean by a race condition, right? And this is my own definition of it, and I think I describe it as concurrent threads of execution acting on a shared resource such that the ordering of operations affects the outputs of the program. Quite a statement. Let's just break that down. So it's concurrent threads of execution. So it might be threads, or it might be processes, or it might be, but it's threads of execution. There's multiple things going on at the same time. In fact, you may well have a single process that has a race condition because it's racing with the outside world in some way. We had one at Undo a little while ago, just in our test framework, and it was really innocuous, silly bit of Python code. It said if what it's called os.path.exists, the path, then recursively remove the directory, and that ran, I don't know, hundreds of times a day for years until eventually, one time, it's running concurrently with another test, and of course, they both just test, does the path exist? Yes, it does. And then both tried to remove it, and the second one who tried to remove it, an exception, the whole test thing fell over. That's just a single-threaded, single process. It's still got a race in it, right? Well, we've got multi-process in that case, I guess. But it might have a signal comes in and interrupts a system call, and you get e-intra, and you don't handle that correctly, right? So we can have concurrent threads of we always have concurrent threads of execution, even if we're single-threaded. Obviously, the more threads and the more processes we have, the more kind of opportunities for this there are. Acting on some shared resource. So yeah, it might be like a piece of data. It might be a piece of shared memory. It might be, like in the previous example, it might be the file system, any kind of shared resource, so that the ordering in which those concurrent threads access that resource affect the output of the program, okay? So I've got these two threads, or two processes, or whatever, A and B, both accessing this thing, and they're in a race, right? And whichever wins the race, it matters, and we're going to get different results. And usually, the one that, usually more often than not, what happens is that you get the kind of 99 times out of 100, it goes this way. This one wins the race because it's doing a little bit less work, it's a little bit faster. But one time in 100 or one time in a million, the other thing wins the race, and then all hell breaks loose. Okay. So hopefully that's all kind of fairly standard. I think probably everyone kind of understands that. That's why we're all here today. But I just want to kind of set the level so we're all kind of at the same level and we're using the right consistent kind of terminology. We're going to look at a bunch of tools, right? I always like to show demos of tools. So we're going to look at ThreadSanitizer, Valgrind, and Helgrind. We're going to look at some of GDB and how that can be useful. Some lightweight logging, which is some stuff that I put together kind of as a result of some of the research I did about how to fix race conditions. I did hear that a few people were doing kind of the same thing. I'm building all this stuff from scratch. So I thought, can't we just make a library and then everyone can use that? And then if we have time, we'll look at time travel, which is obviously something close to my heart. And in particular, something we call thread fuzzing. So I'm just going to use this really simple, this was like the smallest racy code that I could put together without having to think too hard. Okay, so it's a bit of C++20. We're using the J thread here, so these are automatically joining threads. So when this block exits, it's going to join both these threads. So it creates two threads, T0, T1, to two worker threads. I mean, there's the main thread as well. And they're just assigning something to ret and then returning ret. Okay, so clearly this code is racy. Depending on luck, sometimes it will return 0, sometimes it will return 1. I guess actually, technically speaking, it's undefined because C++ data races give you undefined behavior. So like it could, if it wanted to, rm minus rf slash. I mean, that's like a legitimate thing for undefined behavior to do. But in practice, what's going to happen is it's going to return 0 or 1 kind of at random. It won't return 42 because one of those threads, that's going to happen. That assignment of 42 at the beginning is going to happen before either the two worker threads exist, right? But we don't know which one is going to write that out. So let's look at that. So here's my race, so G++, so I have to say standard equals C+20. Always do minus G3 because it's better, and that's it. So if we run this, well, it doesn't print, it returns the result, right? So it's going to return either, that time okay, there we go. So sometimes it's going to return 0, and sometimes it returns, I can actually go, you can see how, so it's usually returning 0, look, but sometimes it will return not, oh, that time it returned, so it's racy. So what did we say we were going to look at first? I think we're going to look at ThreadSanitizer. Quick show of hands, who's used ThreadSanitizer? Ooh, like, okay, half the people, okay. Successfully, well, just a little bit like to use it a lot. Does it work well? Got big smiles and nods here. Yeah, lots of nods. Okay. So for those of you who haven't seen it, let's just see how that works really simply. So it's sanitizer, so we recompile, because it's basically a compiler feature. There it is. Minus f sanitize equals thread. A.out. Oh, anyone seen that before? That's not what it's supposed to do. So I was just preparing this demo. I think I must have updated my laptop, and I was preparing this demo yesterday on the train on my way up, and I was like, oh, shit. Anyway, it's okay. A little bit of Googling. So it's all to do with this mmap random bit. So it's all to do with this address space layout randomization. And the way, I'll get into it in a bit, but the way that ThreadSanitizer and address-sanitizer and Valgrind, Helgrind, all those work actually is by mapping this kind of shadow area of memory so they can track this sort of metadata about the program's memory. And so it gets up, so if you're running on like whatever sort of vaguely latest version of Ubuntu this is, you're going to get into that problem. So we're going to go sysctl vm.mmap. Does that tab complete? Look at that, that does tab. That's quite cool. Bits equals 30, and now whoops. Never type your password while being watched, it's impossible. Okay, now it runs, okay? So now I've got kind of the output I would expect. So it's telling me, sure enough, there's a race here, and it gives me reasonably useful information. It's a bit kind of garbled, but I've got a backtrace, and it's saying I've got a write of size 4, so a write of an int, which conflicts with a previous write here by thread T1 and T2, and these are the backtraces of those writes when they happen, and some information about, here's the backtrace of the threads themselves. So yeah, that's pretty, and it shows me, where's it gone? The line of code. Too much information here, where has it gone? There we are. Race.cpp line 10 conflicts with race.cpp line 9. So that's pretty handy, right? ThreadSanitizer is not part of the ubsan suite. It's not part of the undefined behavior suite, even though it is technically undefined behavior, because it's incompatible. Address-sanitizer and ThreadSanitizer are incompatible. As far as I can figure out, they don't need to be incompatible, but they, it would be really hard for the implementation to deal with that. So you've got this shadow memory, as I said, that is kind of metadata about what the program's memory is doing, and it uses it in one way for address-sanitizer, basically to make sure that no writes are out of bounds and things, and it uses it in a different way for ThreadSanitizer, which is to check that if there are multiple threads accessing the same piece of data, there should be some locks held, right? And those locks should be acquired in the right order, etc. So yeah, you have to kind of do separate builds for ThreadSanitizer and address-sanitizer, which is a bit sad, but there we are. Okay, let's also, yeah, no, I might not have time for that. The other thing ThreadSanitizer does that is quite nice is it will check the ordering in which you take locks. Because obviously if you take lock A and lock B, and another thread takes lock B and then lock A, that's a potential for deadlock, right? And ThreadSanitizer will warn you when that happens. There's another nice thing it does, which is sleep by synchronization, which I'll get to in a bit. So that's ThreadSanitizer. You can do the same with, so Helgrind. Anyone use Helgrind or DRD? 1, 2, 3. Okay, few. Anyone, any reasons to prefer Helgrind over ThreadSanitizer or the other way around?
I think Helgrind gives more. I think it's more precise, gives more.
Do you think it gives more? So there's sort of false negatives with ThreadSanitizer. It won't spot everything.
Memory sanitizer is a little bit, it gives less.
Yeah, yeah.
And it's only Linux, right?
Yes, yeah, great. So sanitizers will work on Windows these days, yeah. And probably Mac. Do sanitizers work on Mac? Yeah, yeah. Anything else? Right. So the performance was called out, and that's kind of the big thing, right? So the sanitizers are way quicker than the Valgrind tool suite. Of course, one big advantage of the Valgrind, I mean, I'll just compile this normally, so I can run it. Valgrind, by the way, if you don't know, it's a suite, just like the sanitizers, and there's not an exact one-to-one correlation between all of them, but it's kind of the same thing. They kind of work in the same way. It's just that Valgrind does it through binary instrumentation at runtime, dynamic. You don't have to recompile your code, but it's kind of slow, and sanitizers do it as a compiler feature, so it's nice and fast. But I can't always recompile my code, right? It's not always possible. But I can just run this regular uninstrumented program like this, and I'm going to get pretty much the same kind of information, right? So yeah, this right of size 4 conflicts with other right of size. It doesn't have nice color printing, so maybe that's not so nice, but it's basically the same. Tells me it's the line 10 and line 9. Some announcements about thread creation, so it's maybe a bit more chatty. There's some of the implementation stuff is a little bit different, but it is basically doing the same job. I have another program here. Let me show you. So that was like just 2 threads being created and doing something really, really small. This program is not much more than that, but a little bit more. So it creates 4 worker threads, and each of the worker threads will just run this looper thing here that just spins around and updates a little. So it looks like this. Okay, so I've got these 4 worker threads, and they're each just updating this char and printing out what it is, so they're all whizzing away. I think it's quite amusing to watch this in Valgrind. Make this a bit bigger. So you can see really clearly, right? It's running 1 thread at a time, and for quite a long time. It's like preempting them after like a second each. Each thread's getting like a 1-second time slice, which is just going to mean everything kind of runs really slowly, and can mean that the race conditions are harder to reproduce. Right, you're changing the way the program is running quite a lot. One thing though, both the ThreadSanitizer and ThreadSanitizer and Valgrind tools, they both have the same thing as the dynamic. You have to catch it in the act, right? And I'll get onto some of that in a bit later. No, so we can see Helgrind going here. Let's watch let's do it with ThreadSanitizer. So sanitize equals threads. So this is now the ThreadSanitizer version of it. And you can see they're all kind of running, nice and quickly. And it's detecting some races, but not as many as I would think. Now, it's interesting. Are these, I guess these, it's a kind of interesting question, I think, as to whether this is a false positive or not. So if I look at this code, it's kind of do very much, but it kind of does what it's supposed to do. I guess for C++, you could argue that is undefined behavior. I don't know. Does anyone know whether it's undefined behavior of a data race in C? I'm not sure that C really says anything about that. So I think I would argue that this doesn't actually have a race condition. It just has a bunch of threads hammering away on some memory, and actually they each update their own entry into this spinners thing. So I think it's a reasonable argument this is not a race condition. What we've got there is a false positive. But certainly what it does is just demonstrates the difference in performance. ThreadSanitizer is still going to run with an observable slowdown, like could be 2x, could be more than that, but it's not. It's observable if you time it. It's not observable to the human eye. We got DRD, which is kind of the same as Helgrind, but just a different implementation. I believe it runs faster with less slowdown, but will catch fewer things, so it's just a little bit less strict. So it's maybe, you could say it's halfway between ThreadSanitizer and Helgrind. So if you've got a race condition, let's just add mutexes until it goes away, right? And obviously, it's not quite so simple. So here's a change to the program that I just showed, and I've got a version of it. I think I've called it that, yeah. So here we are. So let's compile that. And let's do this with ThreadSanitizer. Sanitize equals thread, and Let's run it. ThreadSanitizer has nothing to say about this. But if I do it, I do that thing like I did before, just run it in a loop. Oh, well, look at that. That's actually ThreadSanitizer has made it go away. But I can tell you that definitely, that race is still there. Let's get rid of that. Look at that. So ThreadSanitizer not only says nothing to see here, everything's good, because all the accesses, actually let's show the code, all of the accesses to this shared data ret have this common mutex. So it's not just I was getting unlucky or unlucky there. ThreadSanitizer would not just demonstrate that. Same actually for Valgrind. Let's see if Valgrind will actually.
This is no longer UB, right?
Sorry?
It's no longer UB.
And it depends on your definition of race condition.
Yeah.
Yeah, so
That's why I had a race. That's why I had my definition at the beginning. You see. Yeah. So it's undefined behavior because.
I mean, this is well-defined program, I think. I mean,
Oh yeah, no, it's not undefined. It is well defined because there's always. I don't know actually.
maybe you have two threads and you don't care like.
I'll have to ask.
Maybe one counts later, then you just want to see the last value that came in time, like something like that.
Yeah.
You have several threads updating the value, for example.
So okay, I can see what you're saying. So you're saying it's not. Yeah, it's racy, but it's defined. Yeah. I would still really like my tools to tell me that there's something here if you can, but I understand it's also a very difficult problem. How would it know, right? How would it know what's supposed to happen? How do you know it's not intentional? So, I mean, all of these tools will give some false positives, right? And that's kind of it's just how it is. But yeah, I mean, it could be, maybe I meant that, maybe I didn't. No, you need to go at that, don't you? I always get that wrong. Hang on. No. While Valgrind, do. What am I getting wrong? Echo. What is? Yeah, okay. So that's kind of the same, actually. That's also made. Previously, I've not seen that behavior before. Previously, when I've done it, the race would reproduce. So I seem to have made the race go away by running inside ThreadSanitizer or Valgrind, even though when I run it without any.
The same with atomic variable, for example, if you use the least strict policy for memory order.
Yes.
You will not see the error here either, because it's still well defined.
You will not see the error inside ThreadSanitizer or Valgrind. Yes. Yeah. Okay. Yeah.
Even if you use the last order, because you say like this.
Right. Yeah. So it's well defined, but it's racy.
Yeah.
Well defined, racy.
Well, I mean, if you want that.
You might want that. You might be like a random number generator, right, of some kind.
Well,
So yeah.
By the generator, you have like something coming in time, like for example, statistics or something.
Yeah.
And you just want to.
It could be legit. No, absolutely. Yeah, it could be. Yeah, it could be legit. Yeah. So this kind of gets me to the next thing that I wanted to talk about as a general kind of point. Yeah, that data races. I mean, if you look at any of the kind of, I think there's a lot of confusion between a data race and a race condition. Okay, and people kind of use them synonymously. If we go. So I just looked up just before I came here. Here's the Wikipedia thing for race conditions. It talks about electronic circuits, but then it talks about programming. And this is the example you see every single time, right? We've got basically two threads incrementing some piece of shared data with a read, modify, write, and then, of course, it all depends on the ordering, right? This is the canonical, CS 101 or CS 201, I guess, but, the canonical, what is a race condition? That's a data race. But that's just one kind of race condition. I talked about the race with the file system earlier on, with the checking if the file exists, and if it does, delete it. There's lots of other kinds of races. And in my experience, the data races are like 10% of the races, right? the stuff racing with the OS and the file system and signals and other things is more common. So the thing we've got, a nice little Venn diagram, right? You've got data races, which are just an example of race conditions, which themselves are just an example of non-deterministic bugs, which of course are all example of bugs. And this is another thing I see a lot. So a lot of people, I've seen this many times, they'll see some non-deterministic behavior, fails one time in 100, and they go, race condition, must be a race condition. Well, maybe, maybe not. Could be to do with the dress layout or things, right? There are lots of, so when you're investigating a race condition, a good place to start actually is, let me test that assumption. Is it really a race? And there are ways you can do that. One answer actually is to run it through something like a dress sanitizer and see is there something else wrong there. That could give you similar symptoms to a race. Another one is to try and recreate the failure by messing about with timings. So run stress or something in the background and see if that makes your race, your bug, your non-deterministic bug more or less likely to occur. If it does, it's not proof that it's a race condition, but it's pretty good evidence. There are no hard and fast rules, right? There's just kind of tricks, heuristics, and games you can play. But yeah, it's your race condition may well not be a data race. In fact, your race condition may not even be a race condition. Okay. Let's do some stuff in GDB with multi-threaded programs. So I've heard many times that GDB is no good for multi-threaded programs. I can't use GDB, I've got lots of threads. I never really understand where that's coming from. I think it might be because people don't actually know how to drive it.
It's the developer.
It's the developer. Problem exists between keyboard and chair, right? Yeah.
The cheat sheet is bad, it doesn't happen.
Sorry?
The cheat sheet is bad.
The cheat sheet is bad. Yeah. So let's play with this, with my little threaded program in GDB. So there it goes. So it's all running away. Now, another thing I hear is well, I can't debug. I can't even compiling with debug information causes the race condition to go away. Well, that's not like that. That's extreme. That's just not the case. When you add debug info, you add -G or -G3, you're not changing the generated code at all. All it's doing is adding the compiler will output debug info along with your binary. That debug info, when you run it, not inside the debugger, won't even get loaded. It will stay out on disk. So I don't know, maybe if it's like that's making my binary slightly bigger and that's part of my container and now my container's bigger to spit, maybe, but not really, right? Compiling with debug info will not change your race condition. Mostly running it inside GDB won't even, right? This is running now completely unhindered. Now there's times when running it in the debugger will slow it down. In particular, if there are signals involved, but there are no signals in this program. Or if it's doing things like shared library loads under the hood, when your program does a shared library load, that'll be a kind of hidden breakpoint that GDB will intercept. It will see the shared libraries loaded, and it will start looking at debug info stuff, and then it will resume under the hood, so that'll go a lot slower. But that's not happening here. And generally, most of the time in your programs, kind of once it's up and running, it's not doing shared library loads. So unless you've got signals flying around, this is going to run like completely. You will not be able to measure, I assert, you will not be able to measure a slowdown running like that compared to running outside of GDB. Obviously, if I compile with no optimizations, or very optimized code, that's going to change things. And if I compile with highly optimized, if I compile my binary highly optimized, it can be pretty painful stepping through in GDB. But that's like it's the deal, right? I mean, it's not like GDB's made that worse. You've still got information that you wouldn't otherwise have. I think one reason why people say GDB is not good for multi-threaded debugging is just expectations about what should be happening. So here are my threads. So I've got 5 threads, the 4 worker threads and the main thread. My program has helpfully, oh, by the way, this is just a small thing. Yeah, so just to make this, I added this little call here, pthread set name np. The np is for non-portable, but I've given my worker threads a name in my program so that when it's loaded up inside GDB, there are the names, right? If I don't give them a name, it just gets the name of the executable, this one, threads or a.out or whatever it is. Yeah, so, right, so this is, let's go into TUI mode, I think, because it's a little bit more obvious what's going on. Well, is it, okay, I'm in some futex thing here, futex, wait. But it's because it's, okay, it's in pthread, some sort of join thing. If I frame 4, yeah, okay, so that's where my main thread is, right? It's just blocked in join. So if I do a next, okay, the whole program is running, but that's just not going to stop because it's never, that's not going to move. That's never going to, that's deadlocked, right? Those threads never exit. Control C, I can interrupt it, stops all the threads. Let's go to one of the worker threads, select thread 2. Still, it's, I haven't got any source code here, but I can finish to run to that function's return point. Still inside libc, There we are. Okay. So if I disp this spinners thing, so now this is what's going to be printed on the screen each time. So when I do next, what's going to happen? Is it going to run just this thread, all the threads, stop in a random thread? What would we expect?
I think it runs this thread as much as it can these other threads, right?
So it's going to run all the threads, but it's going to stay inside this thread. I focused myself on thread 2 to focus on thread 2, so it's going to stay here. So when I go next, it kind of makes sense. But look at these spinners, right? So I'm in thread 2, which is the first worker thread. So that hasn't moved on. That's still R. These have all changed, right? So these have all made quite a lot of progress. And now this is going to change from R to whatever letter comes next in the alphabet, S, isn't it? And the others, moving on. So I'm staying in this thread, but I'm just stepping this thread forward. The rest of my program is doing potentially all kinds of stuff, while GDB kind of might single step and runs to breakpoint and does all its stuff, which can be confusing. But actually less confusing than the alternative. So if I don't like that, and you can see why I might not, I'm debugging some kind of fiddly bit. I've got, this, I'm getting close. I've zoomed right in, my linked list manipulation stuff or something. And I step forwards one line and everything changes under my feet. And some things have been added and removed from the list. And it's like, oh, how can I? So maybe I don't want that. So I'm going to do set scheduler locking on. Now when I do a next, it's only going to run the thread that I'm looking at, which might be more, kind of what I want. So, so when I do next, so it's thread, so it's T XGH. Oh, okay, damn it, just done the plus. So it has, but it at least hasn't moved any of the others, right? Do next once more. Nothing. Anyone know why? One of the other thread has the lock on. Exactly. So I can go, let's go out of TUI mode. Thread apply all backtrace. This is quite a cool thing if you don't know it. So it's giving me backtrace for all of my threads. And yeah, look, they're all in some, so thread 1, well, that's the thing that's in join. Here's thread 2. That's in printf. And look at this. GILLL lock wait private. That's some kind of internal libc lock that printf is going to take. This also is inside, this is inside flush. So yeah, one of the other threads has a lock, and I've stopped it running. And so my thread is never going to get that lock, and so it deadlocked. If I can work out probably which one that is just by backtrace. So this one, these all look a bit on a lock, right? Futex. That one looks like it's doing something. I've got no idea why it's doing some AVX stuff, but anyway, it's doing some real work. So thread 3, so that's got I think that's probably got the lock. So it's inside libc code, so I don't have any source code, but here we go. Now, that's got the lock, and I can move, and look at that, it's moving just that one, right? So now I've got control over what's going on. So that's why GDB does what it does. I think it's a very reasonable default behavior, because I think it's going to confuse a lot of programmers if they try next or step over some code and it just gets stuck. The lock, you don't realize there's a lock here, right? It's maybe a bit surprising that printf and flush take a lock, but they do. So the set scheduler locking is useful. You can actually, there's a couple of options. So that's set scheduler locking on. There's also replay is for if you're actually replaying a recorded session. And step is, it does different behavior. So step, if you set scheduler locking step, then when I do a step command, it won't run anything else. But when I do a next command, it will run the other things. So that can also get rid of my weird locking kind of confusion, because, well, no, you'd still get stuck, wouldn't you? But anyway, just maybe that's what you want. Right. Anyone got a reason, and this is not rhetorical, anyone got a reason why GDB is bad for debugging multi-threaded programs? I mean, like, other than it doesn't necessarily give me all the information I need.
It's just hard to.
I mean, it's hard, yeah.
To race conditions.
Yeah. Well, what do you mean by that?
I mean, if error doesn't show up very often,
Mm.
and then.
Oh, like if it shows up like once a day or something. So you could, yeah. I mean, you could just attach GDB and leave it running. And if, you know, again, with caveat of signals, if signals aren't flying around, that should just run, right? It's basically the same, you know, if I run the program from a shell, I've got the shell as the parent just waiting on the program. If I run the program within GDB, I've got GDB just waiting for the program. But if it's not doing anything, not doing any things that cause ptrace traps to return, it'll just run unencumbered. There's some hands up here, yeah.
I think the main reason is similar to what you said earlier in regard to assertions. If I can use TSan or Helgrind and it would directly tell me there's a bug that happens, it's much
Absolutely, yeah.
easier for me as a developer.
Oh, yeah.
Compared to manually having to use GDB to figure out there is actually.
Oh, yeah, for sure. So the response was, yeah, if you're running the sanitizers or Helgrind, it can tell you like much more precisely where the problem is. Yeah, sorry, I didn't mean why would you ever use something other than GDB? There, you know, if the sanitizers of Helgrind will pinpoint your race for you. Excuse me, I got fizzy water by mistake. Now I'm burping. Then that's better, absolutely. But you know, when they don't, so generally, yeah, if you can run the sanitizers, you can run the ThreadSanitizer, and it will find your race. Like that's a good place to start. And if it does, you're done, right? Why would you need to do anything else? But in the case where you can't, let me switch to GDB. Yeah, it's another hand up here near the back. Right, so maybe your race condition is to do with multiple processes, so then you'd need to attach GDB to multiple processes. So you can totally do that. GDB will do multi-process. I won't get into it now, but you can have, just like with multiple threads, you can have multiple inferiors. Inferior, I don't know, it's a very, I think, unhelpful language, but inferior is what GDB calls the thing that you're debugging, right, the debuggee. Info inferiors works just like info threads, and I can attach to multiple things at the same time, or I can have multiple GDBs running, whatever I prefer. Yeah, I don't see why that would be a problem. Yeah, at the back. I'm sorry, multiple GDBs are running?
Then the processes can communicate with each other?
Yeah, if multiple GDBs are running, the processor will communicate with each other just fine. Yeah, absolutely. So if you're talking over sockets or shared memory or whatever, you know, again, if you're using signals for the communication, then all of this kind of everything changes a bit here. But if you're not as long as you're not using signals, then it will be fine. IPC will run just fine. Yeah.
One more question, like when you set schedule locking
Yeah.
on, and after that when you are doing the next, so is it like the next is only acting on that particular thread or all threads?
Right, so the question was, when I set scheduler locking on and I do a next, does that operate on all of the threads or just that particular thread? Just that particular thread. That's the difference between scheduler locking on and off. If scheduler locking is off, when I do a next, all of the threads will run, but it will stay focused within my thread unless another thread gets a signal. I'll come back to that. If I have scheduler locking on, then only the thread that I'm doing next, or continue, by the way. So where are we with schedule? I can't remember if we're on or off, but let's set it on. So continue will do the same. Continue runs just that thread that I'd selected. Yes, question here.
Is there a way to control multiple threads or subsets, basically?
Yes. So thread apply, and you can go thread apply all, or I can go like thread apply 2 to 4. Mind you, can you... what happens if I do that? I have no idea what's going to happen. I wonder. I have no idea what's going to happen. Yeah, don't do that. Yeah, that didn't go very well. You can. I think usually people use thread apply to like. You can go like print stack pointer on certain threads, but can you continue? I want to continue 2 threads and leave the other threads not running. Yeah, I don't know how to do that. I don't know whether that's a thing. Peter.
Does this GDB, just to check, because you're the wizard of this, does it affect any of the process of prioritization of threads by having it in your debugger? The slices that are given out?
Will GDB affect prioritization of threads? I don't believe so. No, I think it will run once it's running. So basically, GDB will attach the process via ptrace, which is this kernel mechanism, which is probably the worst API in the world. But only a few of us are unfortunate enough to have to look at that. And basically then that will mean it's a ptrace attach, which means that, when the kernel's dealing with particularly a signal, and one type of signal, by the way, is I've hit a breakpoint or a watch point, then it will take a different path. And then when there's a signal to deliver, it will sort of look at, the signal to deliver to this process, is it being ptraced? If it's being ptraced, I'm going to send it actually to the tracer instead and let that deal with it. But unless that happens, if that signal doesn't happen, it doesn't go through that path, and all the paths that the kernel goes through will be like unchanged. So I would not expect to see a difference with prioritization.
But I mean, if I'm about to enter a race condition, I'm stepping through the debugger.
Oh, if you're stepping,
that is going to.
Oh, absolutely. So if you're if you're stepping through, and you've got, I don't know, like some really nasty. There's supposed to be a memory barrier and you've got some kind of, memory ordering weirdness and you're stepping each thread in turn, you'll probably never see it, absolutely. But I'm talking about if you just continue all the threads, go to lunch, wait for it to crash, it will run, as long as there's no signals, exactly as if GDB weren't there. Yeah, question.
Is it possible to debug in case of non-deterministic events like interrupts, hardware interrupts, like go to down to the rabbit hole to see if there are special interrupts when it's good?
So for debugging, hardware interrupts, so I'm talking here about debugging Linux userland processes. So when you're at Linux userland, there's not really such a thing as interrupts. There are signals, which is kind of the equivalent at that point, and then GDB will deal with signals in the way that it deals with them, which is a bit weird, but once you understand how it does, it works fine. None of what I'm talking about is kind of all apply to kernel level, actual hardware interrupts. That's kind of hard. I'm going to get to some stuff on that in a bit. In fact, we're kind of running out of time. So let's move on, because there's some other stuff I want to show you. I talked about that. I'll just quickly skip through this. One thing I quite like, I was quite impressed with ThreadSanitizer when I made this change. So just put a sleep in, right? So I'm going to sleep before this thread T1 writes the value. So in practice, this thread is always going to win the race. And ThreadSanitizer, I'm not quite sure how it does this, but I was pleased to see it warned me about that. It said, it looks like you're trying to synchronize with a sleep. And this is always bad, right? Like if you do any kind of, I see it a lot actually, more in test code than in actual code, but people in their tests are, I'm going to do this thing, and then I'm going to sleep for 1 second, and then I'm going to make sure that the thing's done what I expected it to do. And eventually that will catch you out. Question at the back. I'm sorry, I didn't hear. Any coding guidance that automatically detects this? I don't know about at the static level, but like I say, somehow ThreadSanitizer will detect this and complain, which I was impressed by. Yeah, sleep is, you never synchronize with sleep. Always a bad idea. Okay, so as I said at the beginning, last year I sort of did a survey of various people that I knew and went out on LinkedIn and everything and didn't get how do you debug race conditions? And other than the sanitizers and some of the stuff we covered already, didn't really get very much, except a number of people said that they'd been forced to handcraft something because they were kind of, generally I always say that print style debugging is like just lazy and the wrong answer and we reach for it far too quickly. But sometimes it's all we've got, right? Sometimes we can't run with the sanitizers for whatever reason. We can't run it in the debugger because or we're doing it doesn't give us the information that we need. We can't run it, even with our own fantastic WYSI tools that undo because it's going to, the runtime overhead is too much. Maybe I'm on an embedded target. Sometimes just logging is all that I'm left with, and then that's what you have to do. And so sometimes it is the right tool for the job, basically when none of the other tools will work. But as we just saw in my little GDB demo, printf takes a mutex, right? So it's a really bad culprit for the Heisenberg problem. I add some printfs and my race conditions goes away. Partly it's because printf is pretty slow. So it's doing a lot of work, even if I'm only doing it kind of not flat, I'm buffering it and it's not even doing system calls. It's still doing quite a lot of work, so it's kind of slow. But the other problem, like I say, is it's taking this mutex, so it kind of acts as a synchronization point, okay? And it tends to be as I start to home in on the root cause of my race condition, then it goes away, right? Just when I think I'm getting close, because I've now caused some synchronization to happen at exactly the critical point. But so yeah, we can do better. So I took some stuff that some other people said they'd done and thought, yeah. So I made a thing called L3, Lightweight Logging Library. And I was quite pleased with how it ended up working. So let me show you the code. I'm going to go to the code in the terminal, I think, rather than GitHub. It's super simple. It's got the interface is like just L3. There's L3 in it and D in it, and then L3 log. Ignore all the crap. Basically, I'll show you the test code. Probably easier. So, no, that's not what I wanted. Sorry about that. This will do. Here's some of the test code, and where's it gone? So you just do it like this, right? You just call it L3 log hello world. I can give it some arguments, and so it looks a little. Just run it like you would with printf. It's more limited. You can only do up to 2 integer or long arguments, but the way what it does underneath. Let's go to the implementation. Where am I? So it just makes it, it's got an array of these structures. So each L3 log just writes one of these things in, one of these entries into this array that looks like this. It's got TID and it's got the line location where it was and got the message and the arguments. And the logging function itself is super simple, if I can find it. Right, here it is. So basically just gets, so sync and fetch, it adds into the index, gets a slot into the array, and then it just writes in this entry into the array. And one of the neat things it does is it doesn't write the string, it just writes the string pointer. So it's a pointer to the string. And then there's a post-processing step to work out from the pointer what the string literal was. And the outcome of this is, a single-threaded workload, it will do the log in about 1 nanosecond on my laptop, as opposed to hundreds and hundreds of nanoseconds for anything from libc. There's another thing out there called speedlog, spdlog, which is a header-only library. It's quite good. It's quite rich. It's quite a good logging library. It's a bit misnamed and not terribly fast, and it has a buffered mode, so no system calls involved, except it still takes a mutex, and so still can cause those races to go away, and is still kind of slow. I think if I remember, it's sort of again a couple of hundred nanoseconds for a single log in the fastest mode, whereas this L3 is like all it's doing is writing into this array. Oh, and the bit I forgot to say is the array is memory mapped. The array is a memory mapped file. So there's no flushing. Once your program can terminate, and the Linux kernel will just ensure that everything gets flushed out to the memory mapped file, and then you just run this this sort of parse dump tool on that file, and it will give you the nice text-based. So if I no, I'm not going to show you because I got a bit lost in that code. But anyway, yeah, super fast, super lightweight, very simple, and best chance you've got of not hiding your race condition. Yes?
With your logging library, if there's multiple threads hitting your L3, how are you not needing to worry about synchronization?
Yeah, so so it does, Borry. It does. So it does. It's this bit of magic. So it does a sync, fetch, and add. So I've got an array of log entries and an index into that array, and it does a sync, fetch, and add, so an atomic increment and fetch of the index into the array. So it's thread safe.
So relaxed order also important. I think this one is a relaxed memory order.
Yes.
Otherwise,
No, it's just adding one. So it compiles.
Oh, sorry. Yeah, right. But then it's default mode, which is sequential memory order, isn't it?
Probably.
But then all the synchronization happens because it puts the memory per year and
Right. So yes. This is why. So this is why on Linux it does this one. So there is a magic global you can look at called libc single-threaded, which is non-zero if your application is single-threaded. And of course it's thread safe, because if it returns non-zero, then you're single-threaded, so no one else can create any threads, and there's no time of checked, time of use race, because you've only got one thread. And then it just does this just plus increment without any kind of synchronization at all, which is how we get down to 1 second. If there are multiple threads, it goes down this sync, fetch, and add, and then you get to about 7 nanoseconds for the log.
some synchronization happens here.
There is some synchronization that happens here. Yes, you're right. You're right. There is. As far as I think, it's the minimum synchronization that you can do. So it's
I think it's sequential synchronization.
It's like
it's not relaxed synchronization. So
That probably doesn't influence other states.
I think
That's
it
the
does
point.
because
oh no, yeah. So it will, right? But it will cause. So at the kind of machine level, it will do it will lock the bus, and it will have that kind of synchronization. But it's not going to be taking a mutex. Right,
But it
there's-
flashes all the. There's the thing that would
Flush all the.
all the caches and everything like that, because it's sequential synchronization or sequential memory order. I think. Well,
So-
don't quote me on that.
So what I've got, okay, 5 minutes left. So yeah, so I decided that I'd try and write it in assembly to see if I could make it go any faster. So yeah, so it's a locked. So this is actually a trick I found from libc. So yeah, if it's single-threaded, it jumps into the middle of the instruction, so it skips over the lock prefix. But otherwise, it's a lock prefix to xadd. Disappointingly, I had a lot of fun writing the assembly because it's fun. Disappointingly, it goes no faster than the C version. So I am not smarter than the compiler.
So I think lock prefix is the problem.
Yeah,
That's what
it is. That's why you get the worst later. Yeah, but I think without the lock prefix, it's not going to work, right? So I think that's way faster and way less intrusive than anything else you can do. I think, at least I couldn't think of anything that was better. But yes, I mean, unless I might decide, you know what, I'm just going to accept the risk that my log messages might one of my log messages might get missed, but I kind of don't want that if I'm trying to diagnose some kind of race condition. So, I mean, ultimately, we can't defeat the laws of physics here, right? So the Heisenberg principle is a thing.
As long
But
as you're not in a hot loop, you'll be fine.
as long as what?
As long as you're not logging in some sort of tight loop where
Yeah.
it starts becoming
Right.
equivalent.
But if you've got, I mean, certainly, if you've got, I mean, it's definitely, and I didn't try this on a NUMA architecture, so if I've got multiple NUMA nodes all hammering away on that same thing, that could, really cause things to slow down and interfere. But still, I would claim a lot less than, I assert this is the best you can do.
I wonder if you can have a ring buffer for every thread, then you don't have synchronization.
Yeah, I did think about that. Maybe, but then what you want to know, it depends what you're trying to tell, right? So if you're doing just like, I want to do some sort of audit logging that some things have happened, yes. But if what I care about is the interleaving and the sequencing, I want to know, I'm looking for race conditions, so I'm looking for the ordering, so I kind of want that to force it. But yeah, ultimately, that's one of the reasons why race conditions are such fun, is ultimately you can make them go away. Yes, question here.
Doesn't this have a data race on the index? So you're also synchronizing this. So if you have multiple threads all trying
It shouldn't
to log
be.
at the same time.
I don't think it's a data race. No, I think because it's an atomic XAD.
But didn't you use the modulo then later to actually index?
Yeah, but that's after I've got the index thing out. So I could wrap. You mean multiple threads could wrap? Yes. If I've got to have more slots in my index than I have threads running, it's true. Yes. If I had more threads than slots, then I'd be in trouble. I want to show you one last thing before I run out of time that we've worked on that's kind of cool. It's a thing called thread fuzzing. So you want to sometimes we want to make race conditions more likely. So I've got a linked list implementation here that, guess what, has a bug. It's actually a really dumb, simple race condition, but it's designed to do a bunch of work. So if I don't do much work, and it's mostly, then it fails pretty quickly. If I'm doing a lot of work, if I'm doing a bit more work, then it's spending most of the time doing work, and it's you sort of get away with it. The race condition is still there, but you get away with it. That will. Okay, we don't have time. Trust me, that will fail quickly enough. And certainly if I do like 10,000, that's just not going to fail. So what I'm going to do is I'm going to run this with live record, and I'm going to disable ALSR. So live record will make a recording. Which, if you're interested to learn more, you can go down to the undo booth downstairs and see it. Basically, it's going to make a recording of everything that this program does. I was going to run it for a disable address space layer. I'm going to just run that for a few seconds. Okay, it hasn't failed, but that's kind of training phase. Now I can use that recording to learn which bits of memory get accessed by the same threads and kind of infer that this is potentially racy. And I want to cause lots of thread scheduling and put threads to sleep and things around these accesses. So if I now run this again, and I go thread fuzzing analyze, and I go, that's the recording I just created. So we're going to take that recording that I've already created, which was a clean run, and use that to generate knowledge about where to cause lots of thread switching to happen here. So it's going to do that analyzing step, which will take a little while, and then it starts running, and then it fails straight away. Right? So that's a race condition that would take, I don't know, hours to fail normally. By running it through this thread fuzzing analyze step, I've taught Live Recorder about where the kind of racy bits are, run it inside the recording, and now it's failed super quickly, and I've got a time travel recording of the failure. So now the failure becomes really quite easy to, I can see everything that's happened, all the threads and everything. So if I go to the end, here are my, oh, no, that's the wrong one. That's the one that was good. It's that one. So I can load that recording up. So this is kind of like a core file, but it contains everything that happened, not just the state at the end. No, why didn't that work? What have I done? I'll run that again. Live record. Oh, sorry. I've got a 100, 1, 2, 3. Got to give it an argument. So it's not quite as quick. Okay, now it already did crash. Sorry about that. So still, you can see that was pretty quick. Now I can load that up. Go to the end. Here are my threads. What's going on here? Well, item next is bogus, and I can start to like last on that to see when did that change. And it's going to go back and find the last time that, oh, that's not modified in that time. So let's last list head. Anyway, the point is, so here we are. So the point is that I've got now a complete recording of that program execution. This can actually fail in a whole bunch of different ways, it turns out. So I'm not going to live try and get to the bottom of it, but I can step back to any kind of line of code that executed, and I can see the full state. And I can do things like last to go back to when data changed. But the real point was using the thread fuzzing, I was able to reproduce that thread, that race, way, way more quickly. And the other nice thing about it is sort of guaranteed no false positives. Like that is legitimate. That's definitely legitimately behavior that program can execute, can exhibit, and will exhibit if you leave it long enough. We're out of time, I think, aren't we? But I'm happy to sort of hang around and talk anymore. There's a hand up here from James.
Yes, I'm curious if there are data races that the thread fuzzer can find that like ThreadSanitizer would not.
Yeah. Well, effectively, yes, because I can run that in ThreadSanitizer, and the ThreadSanitizer, you have to catch it kind of in the act. The way this is structured, if I run it long enough that it fails, ThreadSanitizer will tell me where the race is. But if I get away with it, because it's just spending all its time doing the work, it never goes through that racy bit, and ThreadSanitizer doesn't notice.
It's like logic error, for example. Like you have everything synchronized well, but you have one case that you missed.
Right. So that's the I haven't here talked at all about static analysis, which probably should have, but yeah, with any kind of dynamic analysis, you've got to catch it in the act. And so what thread fuzzing does is make it much more likely that you can catch it in the act, and maybe even possible you can catch it in the act.
Last thing, if you were working on a legacy code base,
Yeah.
say, there are people who work on those, and you run something like that through it, isn't there a danger it spits out like hundreds of things, but you don't know which of those are?
Yeah, but yes, yeah, it could do. Do you know the worst news? You're going to have to fix all of them, because they're all really in your code. Yeah. Right, that's the thing. No false positives. Like those things can happen, and if you run your code for long enough, under enough load, they will happen. So if it does, that's now you just know how fucked you are.
But not the order that you've done.
No, that you have to figure out. Yeah, there's some. Yeah.
Wanted to read one question from the online audience because they have been neglected for a long time. So the question is about the sanitizers.
Yeah.
The person who writes, I have a project where it provides shared and static libs using LTO and address undefined sanitizers, but the shared libs give ODR errors, so one definition rule errors, when using address undefined sanitizers. It has no problems with static libs, also the errors for ODR refers to a name that does not exist in my code anywhere. So the question is, was it wrong to use address or undefined sanitizers for shared libraries when using LTO?
So is it wrong to use address sanitizer for shared libraries when using link time optimization? I don't think that's wrong, and I mean I don't know, right? It's quite a lot of the question. I've got no idea. But my immediate reaction, very quick answer, would be there's probably a problem, and you should figure out why it's bad. I'll give you a little anecdote. You know the XZ, the brilliant, frightening, terrible, awful XZ attack from last year, whenever it was? Red Hat caught it using Valgrind. It was a Valgrind failure for some uninitialized data in XZ. And unfortunately, one of the XZ maintainers came and fixed the Valgrind error, and then it went out and got spotted by the guy at Microsoft who noticed that the SSH was going slowly. So, moral of that story is if Valgrind or sanitizers or anything else is telling you something's wrong, like maybe everything's fine, but that's like I'm in my house and I smell smoke and maybe it's all fine. Like Yeah, but you really ought to figure out what's going wrong. And the chances are that the person who wrote in online, I would gamble, has a problem, and they ought to figure out what's going wrong. Yeah.
We'll have to stop now.
Stop. Yeah. Okay. I mean,
Take questions.
Yeah, I mean, I'm happy to sort of hang around here and have any questions or anything, and then we'll kind of let everybody else go.